somebody you'll eventually discover there. Sorry, I disappeared for a minute. That it's hard to come up with a loop invariant, and in order to help with that, years ago, I came up with a number of loop invariants that usually the loop invariants we care about are. So there's kind of more of the input, more of the output, narrowing the search space, shrinking the input, sort of data structures. So those are classic ones. If you ask, I could ask you, for this problem, what is the more of the input loop invariant? You should be able to tell me. But right now, we're going to cover a much more loosey-goosey loop invariant, where it's talks about fairy godmothers. And you know, as soon as you talk about fairy godmothers, it's going to be a little loosier-goosier. So what this one is, you know, I say you fly in from Mars, and by that, what I mean is that suddenly you're at the top of the loop, and all you know is, you don't know how you got there. All you know is that the loop invariant's true. And so somebody made that true for you, right? And you're just trusting that it's true. So in this type of loop invariant, I'm just saying, jump into the middle of the computation and think about what would I like? What would I like to be true? And asking for that, all right? So let's go through the problem. I was at a conference in Germany at a castle about cake cutting, and somebody told me this problem. So there's a round lake, and you or me, here I am swimming, and there's a monster, and the monster wants to eat you, and your goal is not to get eaten. So what are the information about your superpowers? Well, your one superpower is that you can run infinitely faster than the monster. So your only goal is to get to the shore without the monster there. And then you can run away. So here you go. Here you go to the shore, and he's running after you. And the question is, does he eat you or not?
Professor?
Yeah?
Yeah, I have a question. So is I swim in a direct line or I swim in circle?
All right. Well, why don't you wait until I tell you more, because basically you have the choice of swimming however you want, right? So let me tell you more about the problem. You have the power to swim. He has the power to run. And we want to see who's going to eat who, right? So we need some more facts. The other fact is that the speed at which he can't swim, so he won't enter the water. So as long as you're in the water, you're safe. But you also have to get out, right? Eventually. So the other fact is that he can run 4 times faster than you can swim. All right? So let's talk about various algorithms. The one option is, down here. The one option is you start in the middle because, I don't know, that's a good place to start. And you pretend that the lake was radius 1 and your speed was 1, and you just swim straight to shore. Then it will take time 1 for you to get there. But the monster, presumably he's opposite where you are, where you're running to. So he has to run around half the circle, right? So the half the circumference is pi, but he runs at a speed of 4. So his time is less than 1, and so he eats you. Everybody understand that? So that strategy, as the person asked, do you need to just swim straight? Well, if you swim straight, you will be eaten. So you need to come up with another strategy, right? So what's the other sort of you're able to do is, well, you're able to watch him, and based on where he is, you get to choose which direction to swim. But on the other hand, he's watching you, and based on where you are, he's going to change what he's doing. And the question is, do you have a strategy in which no matter what the monster does, you're guaranteed to get away from him? All right, everybody get what the question is?
Yep.
All right, so the stuff here at the top is what I added the other day. I wanted to put it in the context of our steps, so you're clear what the steps are. So the first step, which I probably will do for you, is I give you the precondition and the postcondition. So the precondition is the little house that says what's true about the world when we first arrive, and the school is the postcondition, what's true when we're done, right? So the precondition we can have is, well, I'm somewhere in the lake. He runs 4 times faster than I could swim. We could list more details about the problem here, but we kind of get the setup. And what's the postcondition is I get to the shore and he's not there, right? Everybody get the problem? All right. So the two things, if we're going to make a loop invariant algorithm, then you have to follow the various steps. And the first step is to come up with a loop invariant, which is a picture of where we're at. But I decided another thing that's good to have some sense of is what your measure of progress is. And what a measure of progress is, you should know, is given a picture of the state of the universe, it tells you a number, a real number, a measure, which tells you your measure of progress, right? And so, well, you can imagine a lot of different measures. You can ask, how far am I physically from the monster, right? It could involve where the monster is. It could involve where you are. It could involve how far you are from the shore. You can imagine lots of different measures of progress, but I'm going to tell you that my measure of progress is simply how far am I from the center, all right? That's going to be my measure of progress. And you'll see from the loop invariant why I don't include where the monster is, right? Because certainly having the monster far away makes me feel happier. But we're going to put that into the loop invariant, all right? So we need to, what's a loop invariant? Remember, it's not an action. It's a picture of what's true right now. So, and we're doing fairy godmothers. So this is what I'm going to ask you guys. You're right there, right? And the monster is somewhere, and we're going to ask the fairy godmother to put the monster where we want to put him. And where are we going to put him?
Right, so like opposite direction.
Exactly, exactly. Now, in some ways, you're not asking for enough, because if I could ask the fairy godmother, I would say, I want to put the fairy godmother, I want to put the monster in prison somewhere, and I want to be in bed, right? That's what I would ask if I could ask anything. But presumably, we know there's no way of getting, the monster is always going to be on the shore. So given he's on the shore, that's where we want to put him, right? So that's our loop invariant. Is you could word it various mathematical ways, but one way to say is you draw a line from where I am to where the monster is, and that line should pass through the center, right? Everybody buy that?
Would it be possible to say, like, I want him to place the furthest possible place from me on the shore?
Yeah, that would be identical. That would be identical. And hopefully the TA would be able to translate from one to the other, right? I mean, the way, I don't like yours quite as much, because yours in some ways requires me to do a calculus problem of maximizing where I'm actually telling you where he is, right? But same idea.
I have a quick question.
Yeah.
I'm just trying to compare this to the sorting one, the loop invariant that we did. You know, so that one was like, you know, you're halfway through some iterations, half of it's sorted, and some of the input is not sorted.
Yeah.
Then the next iteration, you take another input and you put it where it needs to be, and now you have more sorted stuff.
Yeah.
So if you look at this, in this loop invariant, I mean, if he's already opposite of you, like what would like an iteration be then?
Well, that's what we're going to do next, right?
Okay.
Right? So here, let's bring up the next thing. What is our goals, right? These are the classic goals. I have to figure out how to establish the loop invariant. I have to figure out how to maintain the loop invariant while making progress. I have to make sure that if I make enough progress, then I will exit. And then I have to prove that if I exit and I have the loop invariant, I can get the postcondition, right? Those are our steps. And so let's go through those steps. So here is, and you can do those steps in various orders. I tend to do the maintaining the loop invariant one first because that's the one that is going to likely tell me quickest whether I have a good loop invariant, right? But this time I did it in the order of the algorithm. So it's the same, all right? So what does this one say? We're trying to establish the loop invariant. So the picture is my little icon that the house says the precondition is currently true. The step means I'm going to take some action. And what do I need to become true is the green is the loop invariant. So I need to make the loop invariant true, right? So what you write down on your test paper is exactly this. And then you start filling in things, all right? The first thing you can fill it, right? So what do I got here? This is just a reminder not to drown. And what do I mean by that? People tend to panic and drown. And so this is a good place that you might panic and drown. You might say, oh, what do we'll talk about panic and drown in a minute. Let's just say, what do I mean by it, right? Don't try to solve the whole problem. Don't try to escape. Don't try to make progress, right? Don't try to do anything that you think you might want to make. The only thing you need to do right now is to do the easiest possible work to make the loop invariant true, all right? So what you're going to do is you're going to say, great, what do I know from the precondition? Well, I'm somewhere. What do I need to achieve? What's my loop invariant? Well, he's opposite of me. So it's kind of the picture I have right here. Suppose you're here, you're somewhere, and he's here, he's somewhere, and now you got to get him opposite of you. So what many people will do is they will say, well, see, I got to get away from him. I will, and you think of various ways of getting away from him. And that becomes as hard of a problem as the original problem, right? So you want to let all that go and just say, what's the minimal thing? All I care about is establishing the loop invariant, right? So is anybody who hasn't read this know how to do it? Just think about how to do it.
So the swimmer has to just turn around, have their backs back again against the monster.
Yeah, no, because you're saying he's behind me. So all you have to do is turn around so he's behind you. I need him to be opposite of me. The loop invariant says if you draw a line from where I am to where the monster is, that line goes through the middle, right? So that's if I'm here, I need him to be on the opposite side.
So
right?
Go to the center of the lake and then do that.
Yes, exactly. So what is my action? So let me tell you some motto, thing. I'm religious, very religious about various things. And one of them is that I really, really like the number 0. So as a rule of thumb, whenever you see a problem, you think, what is the 0 of this? What is the empty set of this? What is the empty tree of this, right? So here, the 0 is kind of, I'm in the middle, right? Now, then you have to think, right? So that's my code is move, bless you. My code is to move into the middle. And does that make him opposite me? Well, my official definition is you draw a line from where I am to where the monster is, and I don't care where the monster is, And well, does that line go through the center? Well, it does kind of, because I'm sitting on the center. Now, the one voice was saying, oh, you have to turn around. Well, certainly the direction you would want to swim is away from him. So yeah, you want to turn around. But the loop invariant doesn't talk about which way you're facing. It just says, is he, this definition of opposite. So everybody good with that?
Wait, sort of a confusion right here. So then, are you saying that so then in the precondition, you're saying that you are somewhere in the lake, right?
In the lake, yeah.
Can you also say that the precondition is you are at the middle of the lake?
You could, but you're changing the problem. The reason I didn't say that is because I wanted to add this extra twist of how do you make the precondition, the loop invariant true, by swimming to the middle. And certainly you can imagine if you started like this, right? You're swimming because you're casual and you don't notice him until he gets close to you, right? And I was once in Brazil when we were just swept out from the ocean. We were swept out. And what I've always been told is you don't try to swim into the shore, right? You have to realize that there's this riptide that's swimming you out. So how do you deal with that? So in this case, your first thing to do is not to try to swim the shore because he'll eat you. You just ignore him and swim to the middle, right? That's how we begin.
Professor, can I ask you a quick question?
Yes.
So if is it possible, for example, to just kind of like, since if monster cannot slow down and you cannot slow down, keep a constant speed 4 times faster when you swim,
yep.
Can't you just swim in a concentric circle like very slowly? And since he goes like 4 times faster all the time, eventually, if you go like kind of like another concentric circle, eventually you're gonna go to shore because
no, he can run any speed up to his fastest speed, right? I mean, he can walk too.
Okay, that doesn't work. Okay.
I'm just talking about his maximum speed. If you follow the shore, he's going to follow you. Come on.
Okay,
right?
Thanks.
All right, everybody get the establishing the loop invariant. All right, we're in the middle. Now, what do we want? Right, here we got it. Right, so we established the loop invariant. Now we're going to do maintaining the loop invariant. All right. So when you want to do that, you say, I know the loop invariant's true. I know the Exon condition is not true. I'm going to do a minimal action I have to do 2 things. I have to somehow make some kind of progress, and I have to have after the iteration the loop invariant's true or not. So I'm going to give the same hint. Don't panic and drown, right? Don't try to solve the whole problem. Your goal now is not to escape or to make progress, right? In fact, generally your goal is to make progress as well. But right now, let's not try to make progress. Let's just try to maintain the loop invariant, right? So he moves a little bit. Say he moves clockwise. What are you going to do?
Move counterclockwise.
Counterclockwise.
Yeah, I have to think about it. I was thinking about that. No, I think you're both moving clockwise, right? Anyway, you can see here, fill in what we know. What do we know from the loop invariant? We know that he's opposite of me. What do we need to do? He needs to still be opposite of me. What is our action? Well, you can see, you kind of move him. So when I was this morning, I was saying he moves this way. You want to kind of move perpendicular to his movement, right? So yes, you're moving in the opposite direction, but you're on the opposite side of the circle. So you're both moving clockwise. But you can see here we watch our video again, right?
So does that? Are you kind of saying that you always want to keep your back towards the monster?
Yeah, I'm going to stop. I don't know if it's you, but somebody keeps talking about where your back is. And yeah, that's true, but I never talk about which way you're spinning, right? You could be doing the backstroke and facing him. You could be doing I don't know where your head is. I'm just saying you're on this circle and you need him to stay opposite of you. So if he moves slightly, then you move in the opposite direction.
Yeah, so swim the opposite direction that kind of he's like going towards.
Yeah. If he moves
a little
that
bit
way
to the right, you move a little bit to the left.
To the left. Exactly. Right.
Did we not have to break up the distances into the epsilons?
Yes. Well, yeah, you could do it. He moves an epsilon. What do you do? Right? You could do that as well, because this is a funny problem where it's continuous, right?
Yeah.
So, yeah, maybe we should be doing, right? If he moves it, maybe what you do is you change it every time he changes direction, right? If he goes straight full speed for a while, then how do you respond, right? But we're not going to worry about that so much. Tell you the truth, if you want an optimal solution, we're not going for optimal. But optimal, you'll have to do some really hard calculus and differential equations. And 10 or 20 years ago, when I first saw this problem, I did spend some time. I got the easy solution fast, but I did later spend some time coming up with an optimal solution. And that you definitely have to do some sort of epsilon calculus. But let's not do that right now, right? Let's just say, right, if you can swim opposite of direction, then you can maintain the loop invariant, right?
Yo, who's screaming? Who's that in the background?
Yeah,
can you guys turn off the mic, please?
Hello.
Yeah, good. I think we're
Thank
good.
you.
So you can unmute yourself if you want to say something, but if there's noise in the background, turn off as soon as you stop saying things. All right. Everybody get this? Now, what do we got? Yeah, there are various problems with this that you might notice. The one problem is he runs 4 times faster than you, right? So we have to deal with that. The other problem is that I also need to make progress. So how do I make, what's my measure of progress is how far out I am. So we're going to solve that second problem to say, well, not only do you follow the little circle back and forth as he's doing in the opposite direction, but you also have to spend some of your energy spiraling outwards, right? So we're going to say you swim in the opposite direction and you have to move outwards somewhat, right? So if you can manage that, then yeah, we're maintaining the loop invariant, right? But the question we ask is, how long can we do this? Can we keep doing it? Certainly if we sit in the middle, he can spin around and I don't have to do anything, right? But how long can I maintain it? And said another way is, when should I exit my loop, right? And coming up with an exit condition is sometimes tricky, but my advice here is one place to exit is when you don't know how to maintain the loop invariant anymore, right? Why is that? Because, right, what you need to do is you need to keep iterating, is looping, as long as every time you iterate, you need to maintain the loop invariant. So if you can't maintain the loop invariant, then you better not loop anymore, right? So that's what we're going to just say here. Let's have our exit condition be that you can no longer maintain your loop invariant for some reason. And so if the exit condition is not true, then almost trivially, right, we can maintain our loop invariant. All right, so everybody good?
Can we not have the exit condition be me reaching the shore?
Yeah, that would be great. That's certainly a great loop invariant exit condition, right? Because that's when, it feels like we're done. But I don't know how to maintain, if you're near the shore, then you can't maintain the loop invariant, right? So in order to that to be your loop invariant, in order to have your exit condition be that you you reach the shore, then you need a much more then you need to be spiraling outwards, and you need a much more complicated loop invariant as he gets closer and closer to you. But let's just do it this way, all right?
Okay.
So let's do some math here, right? Here, he's running on this outer circle. You're swimming on this inner circle with radius r. We're assuming our pond is radius 1, though you could scale everything up, right? And let's see what happens, right? So how far does he run? In this picture, he runs from there to there, right? So let's give that a name. Let's say he runs distance d, right? Now, how far do I run? How far do I swim? Well, I swim that little bit right there, right? That little arrow. So we have to calculate how long that is. Well, one thing that's useful from high school geometry is to always look for similar triangles, right? Here's a triangle, here's a triangle. Why are they similar? Well, because this angle clearly equals that angle, and because it's sort of it's sort of a, what do you call it when it's this side is equal to that side, right? I mean, they just feel like they're similar triangles, right? So if they're similar triangles, then that means the one is a scale up of the other. So if to go from distance d to distance, here I'm going distance 1 to distance r, that multiplies by r. So to go from distance d to this distance, I again multiply by r. And so this distance here is r times d. And remember, of course, r is less than 1. So r times d is less than d. Right? Everybody buying that? And of course,
could you repeat that again? I just didn't really I didn't understand that. Sorry.
Yeah, well,
R is less than 1.
R is less than 1, right? Because the whole distance is 1, and I'm less than it. If r was 0, then I would be at the center of the circle, and my distance I travel would be 0, right? 0 times d. If r was 1, I'm way out here, then I'm traveling the same distance he's traveling, right? d. But since I'm on this smaller circle, I don't have to travel as far. One way of thinking about it is, suppose he ran all the way around, right? And then I have to swim all the way around. So if I'm in his distance is the circumference. So what's my distance circumference? Is the circumference of the circle that's r times smaller. So my distance, the circumference of my circle, is r times the circumference of his circle, right? But more generally, I'm talking, if these are similar triangles, then I can scale this triangle to be this triangle by multiplying by r. So 1 times r, it gives me r. d times r gives me r times d. Right? Does that make sense?
Yep.
And just let you know, certainly during a 24-hour test, I may let this go and expect you to do it. But during an hour-and-a-half test, I would never expect you to do this math on your own.
Okay, good. Thank you. Because it's a little bit over my head.
Yeah. Well, it shouldn't be. It's something you should have learned in high school. But all right. So now, he also moves 4 times faster, right? So how much time does it take him? His time is d divided by 4, because he's moving at speed, say 4. And my speed is 1, so it takes me rd time, right? So what do we need for me to maintain it? Is we need his time to be less than my time. No, my time to be less than his time, right? If my time is less than his time, then I can manage it, right? This is the time it takes him to do it. This is the time it takes me to do it. And if it takes me less time, then I can do it, right? In fact, if it's strictly less time, then I have extra time with which to move outwards. So let's solve this equation. We have a d on both sides, so let's cancel d. And we see what we need is for the radius of the circle to be a quarter, right? And that's just back to saying this circle is a quarter the size of this circle. So in the time it takes him to run around, I can swim around, right? Because he's 4 times faster, he goes 4 times longer. So my circle is a quarter the size of his circle, right? Does that make sense? And that's the bottom line. As long as the circumference of my circle is less than a quarter of his, then I can maintain the loop invariant, right? So that's what we're saying here, right? If it's strictly less than a quarter, and then I can swim my circle faster than he can run his. And if it's strictly less, then I have extra time, right? So I can maintain the loop invariant like that. And if it's strictly less, I have extra time with Mitch. I can also swim outwards. So watch here, he's going to swim out there, right? There, I just swam outwards, right? Does that make sense? So let's recap the maintaining the loop invariant, right? What are we saying? We're saying as long as my circumference is less than a quarter, then I'm good, right? But if the circumference becomes a quarter, then I can maintain the loop invariant, but I can't make progress, right? So what am I going to do? I'm going to exit, right? So here, my exit condition is going to be I reach a quarter distance. So if I haven't exited, then I'm less than a quarter, and I will be able to maintain the loop invariant, right? Everybody good? So now, let's say when I get to the quarter mark, right? What do? I can no longer maintain the loop invariant. And so what I'm going to do is I'm going to exit my loop. Now, have I solved the problem? No, I haven't gotten the post condition, right? But I'm going to exit the inner loop. And then what do we have to do is we have to do this ending thing, right? So what does it say? It says, we know the loop invariant is true because we've maintained it. We know the exit condition is true because we've exited. We have to do a minimal amount of work to get the post condition to be true, right? So if this is true and this is true and you do this action, then you have to prove that then the loop invariant would be true. So let's do that. What's the loop invariant? He's opposite me. What's the exit condition? I'm at the quarter mark, right? What's the post condition? Here, this is how you do your test, right? How you do your test is you always write this down, right? And then you fill in what you know, right? What I know the loop invariant is he's opposite me. I know the exit condition is I'm at a quarter. I know the post condition is that I'm at the shore and he's not there, right? So what do I have to do is I have to come up with some code, some action here that's going to get me from this picture to me on shore, right? And at each point, we don't want to do anything too fancy, right? You might say we could spiral, we could do all these fancy things, right? But what is the easiest thing that you might do?
Just swim across.
You just swim for it, right? Let's see if that works, right? If we swim for it and we see it doesn't work, then we're going to have to do fancier things, right? But for now, let's see if that works. So let's do the math. We swim for it. And what does swim for it? What does that mean? Oh, here we go. Swim for it. Oh, here we go. Swim for it. Right? That's what's happening, right? You're swimming to shore in a straight line, and he's running around. And the question is, does he eat you or not? So let's do the math. Now, how far am I swimming? Well, I'm already at a quarter. So I only need to swim a quarter distance. Let's say I'm still speed 1. So it takes me a quarter, it's not quarter, 3/4. I have to swim 3/4 distance, right? Because I'm at a quarter. I swim 3/4, it takes me 3/4 time. What about him? He has to run half the circle, right? Because the loop invariant, remember by the loop invariant, he's opposite me, right? By the exit condition, I'm at the quarter, so I only have to run 3 quarters. By the exit condition, by the loop invariant, he's opposites me, so he has to run all the way around. So he has to run a distance of pi, 4 times the speed. So you divide by 4, and those are our 2 numbers. And look at, I got there just before he did, right? Everybody buy that? So I win, right? Swim for it, and we solve the problem. Everybody got this algorithm?
Jeff, just a quick question. So when you're at 3/4 radius, could you just point where that is on that little circle? I'm trying to visualize it.
Oh, well, don't expect my scaling to be right.
Okay.
But there, you see the mouse is at the center,
Right.
right? And the distance to the shore is 1. And you're on a circle whose radius is a quarter, right?
Right.
So how to get from the quarter circle to the shore by the fastest means, swim for it means swim for shore in the fastest direction, which distance will be 3/4.
Oh,
So
I
from
see.
the
Okay.
so from the edge, like the edge of the circle that we're
Yes.
at to the
Yes.
shore, that's 3/4.
Yes.
But yeah, okay. If we're in the middle, then that would be 1.
No, right? But if we're in the middle,
Is 1 radius.
then we're in less than a quarter. So we don't exit the loop, right?
So where does the quarter come from?
Well, I've decided that quarter is the quarter comes from this math right here. I want to say I'm on some circle of a radius r, and I want to swim, I want to maintain the loop invariant, meaning if he runs this distance, I have to run this distance, right? So this is the picture that's required for me to maintain the loop invariant. So if he goes some distance d, then you do the triangles, and I'm doing some distance rd, right? But he's going faster, so he does it in times d over 4. I do it in times rd. So I need rd to be less, I need my time to be less than his time, right? The other way to think about it is it does kind of make sense. If this circle is a fourth, the radius of this circle is a quarter, the radius of this circle is 1. So the circumference of the little circle is a quarter of the circumference of the big circle, right? So he has to run, if he's going to go all the way around, he has to run 4 times farther than I do, right? So he goes 4 times fast. So if we're on the quarter mark, right? If we're actually on the quarter circle, then I can just maintain the loop invariant of staying away from him, right? If I was in further, if I was a little closer in, then I could maintain the loop invariant faster than him. And so I have extra speed to go out.
I have a question.
Yeah.
So the reason because it has to be less than 1 over 4 is because once you get to the radius that's a quarter, then you no longer have that extra time to make progress. You have to continue and for that time to keep the loop invariant, but you don't have even time left to make progress.
Yeah. If you're at a quarter, if you're exactly at a quarter, then you can maintain the loop invariant, but you can't make progress. And we have to maintain the loop invariant, and we need to progress. So as soon as we're at the quarter mark, hey, dude, you got to do something else, right?
Yeah. Okay.
Right. This is saying this tricky algorithm will get you to the quarter mark, and when you get to the quarter mark, you have to do something else. So what are we going to do instead? Well, let's review what's true when we're doing something else. Well, we know the loop invariant's true because we've maintained it. We know he's opposite of me, right? We know we're at the quarter mark. Why are we at the quarter mark? Because we exited. That's our exit condition. We don't exit until we're at the quarter mark. Now, I'm not saying I'm exiting the program. I'm exiting the loop, right? Now I'm after the loop. I have this code after the loop. And what it needs to do is it needs to get me to shore without him. And how are we proposing to do it? We're proposing to swim for it, right? And we do the math, and the math says that if you swim for it, you will get there just before he does, right? But luckily, you know how to run infinitely fast. So the minute you get to shore, you're gone. Everybody buying this?
Yeah.
Yeah. So that
Yeah.
quarter mark is at that edge of the circle, right, Professor?
Hmm?
The quarter mark is at that edge of the circle on that radius? Yeah, right there.
Quarter mark is all the way along here. It's the red circle.
Okay, that's the quarter mark.
The red circle. You're somewhere on. Yeah, if this circle, if the lake is radius 1, and this red circle is radius 1/4, which I don't know if that's true or not. Maybe it is. Then that's where you are.
Okay, cool. Thank you.
Right?
Do we just assume that we'll be able to get to the quarter mark?
Nobody. What did we do? Let's review. First, we said what our loop invariant was, that he's opposite you, right?
Mm-hmm.
And then we established the loop invariant. How? By swimming into the middle, right?
Yeah.
So now we're in the middle. And the joy with that is that the loop invariant's true. All right? So now, what's the loop invariant? The loop invariant's kind of, well, he's opposite to us, and we're in a circle whose radius is less than 1/4, right? Because all right, so here, now we're saying we flew in from Mars. We don't know how we got where we are. All we know is that the loop invariant's true, and the loop invariant says he's opposite of me, and the exit condition is true. And I'll tell you in a minute, the exit condition is that, right, we get past all of this. And what is the exit condition? The exit condition is that you exit when you're at 1/4. So if you haven't exited yet, then you know that you're less than 1/4 radius, right? You're somewhere inside of this red circle, right? So what do you do if you're somewhere inside of this red circle? You maintain the loop invariant by swimming opposite it, which we proved you can do, and you have extra speed with which you'll swim out, right? So what's this loop's going to do? We're proving that you can always maintain the loop invariant while making progress, right? So you'll keep doing that. You'll keep doing that. You'll keep making progress. And what's the progress? Our measure of progress is your distance out, right? From the center. You start with progress 0, and we guarantee that you keep increasing your distance out. So eventually your distance will get to be 1/4, right? And when you're so then what's true? Then I know the loop invariant's true. Why? Because I've been maintaining it. I know the exit condition is true. Why? Because my exit condition is 1/4. I've exited, and now I'm panicking. I need to do something different, right? So I'm at 1/4, so I'm going to exit my loop. And now I know these two things are true. And so what do I do next? I swim, right? And we do the math, and that proves to me that I get the post condition. So do you see how there's 2 stages of the algorithm, right? Well, 3 stages of the algorithm. The first stage is establish the loop invariant. How do you do that? You move to the center. So the second stage is spiral outwards so that he's always opposite of you and you're moving outwards. Third stage is when you reach the 1/4 mark, then swim direct. That's the algorithm.
Yes, but we assume that we'll be able to get to 1/4 because in the algorithm we took RT less than D/4, which we did not have any reason to believe because when we were moving in the red circle, location of the monster was also changed by d, which we never factored in.
I don't like what you're saying. I didn't completely understand what you're saying, but there certainly are parts of it I don't like. The one part that I didn't like is you said we're assuming that you can reach the quarter mark. And no, we're not assuming. We're proving that you can reach the quarter mark, right?
Yeah, but that's like, we are assuming the loop invariant will be true. We are proving the loop invariant will be true.
Proving,
we are kind of...
I'm proving that we can get to a point in time in which the loop invariant is true and the exit condition is true, right? How do I prove that? It's over here, right? Right, so what do we prove here? We prove, suppose you're in a place where he's opposite of me, the loop invariant is true, right? Suppose you're in such a state. And suppose the exit condition's not true, so I'm less than a quarter, then I don't have to worry about the entire algorithm, right? The whole algorithm is complicated. So I'm going to just worry about, let's go back to what some guy said, do we divide it into epsilons, right? Let's divide it into epsilon time periods. And all I have to worry about is my one little epsilon time period. So I have to say, where am I at the beginning of the epsilon time period? And do I do the right things during those epsilon time periods to accomplish my epsilon time period goal? All right? And you don't want, if you worry about the entire algorithm, I promise you, you'll drown. So we're going to have a separate goal, separate precondition, postcondition for every epsilon time period. All right? So during this epsilon time period, I have to know, it's like relay race, where you have your friend has a baton and he runs around the track and then he hands it to you. You know that kind of
yes.
race?
Track and field.
Track and field race, right? So imagine it's like that. Your job is to take the baton from your friend and to run around the track. Is it your job to help your friend run around the track the first time? No, that's not your job. Your job is to assume that when I start my job, my friend is handing me my baton, and then I'm going to run around the track. That's my only job. And what I'm asking you is not to worry about other people's jobs or you'll drown. All right? So what we're going to do is we're going to first make sure that everybody does their job. In every epsilon, the correct job is being performed. And then we're going to put all the epsilons together and make sure that together it solves the whole problem. All right? So let's
take one step at a time.
Right now, we're going to take one step at a time. Yeah. So when he hands me the baton, I have to know, what does that mean? What does that tell me? Well, handing me the baton means that I'm somewhere in the lake and he's promising me that the baton promises me that the monster is as far from me as possible, given where I am. The not exit condition is promising me that we have some property. And the exit might scare you here because you might think that we're exiting the program, but we're not exiting the program. We're only exiting the loop. So since I know that I'm not exiting the loop, I know that my distance from the center is less than a quarter, right? So what is my goal? Is just to take an epsilon step. During the epsilon step, what happens, right? What happens is he runs some distance. And we're assuming that he's running a steady distance. Why? Because it's only an epsilon period of time. But even if he backtrack, it's only going to make our life easier, right? He may run some distance, and I say I have to run that distance. And am I able to do it? Well, you look at the math, and as long as the radius is less than a quarter, I can do it, right?
Professor, so before it reaches a quarter, you're kind of swimming like on a curve.
Yeah.
Opposite of the monster.
Yeah.
And then right when
Yeah.
you hit the quarter mark, you just go straight.
Yeah. Yeah.
Okay.
So he's talking about a spiraling kind of back and forth. But I mean, the way I actually talked about it is you do two things. You swim on your little circle, and then when you have extra, you take whatever extra time you have is you swim outwards, right? And if we did that in an epsilon way, it would look like a spiral, right?
I drew a diagram. It's something like this.
Okay. Oh dear.
Is that the spiral you're talking about?
Oh yeah, sure. Yeah, but it won't make it all. Yeah. So if you were doing a more fancy algorithm, you would be making it all the way to shore, right?
Yeah, that's what I was thinking originally.
Yeah, but you know, as you do that fancier algorithm, you're not going to be maintaining. You'll be maintaining the loop invariant only until the quarter mark, and then after the quarter mark, he's going to start catching up with you.
You would need some other loop invariants.
Yeah, we need to say, oh, where is he as a function of where I am, and you'll have to solve some differential equation. And I spent an hour once trying to do it and failed. All right. So my advice is let's not do that.
Okay, so is the reason why we end up changing the action that we're doing, which is like swimming the opposite of him, is it because if we keep doing that, we won't make it even after the quarter mark, we won't make it and he will catch up to us? Or is it because it after the quarter mark, the loop invariant can't be true anymore? Is that
yeah.
So it's the loop invariant that basically like stops being true after the quarter mark. So that's why we have to do something else.
Do something
else.
It's
true.
Right.
Okay.
Right. And so we're going to just try doing something else. And what's the obvious do? What's the panicky do something else is to swim for it, right? Our fine Verge, you know, the guy who gave us the picture, he's doing a fancier something else, which is more optimal, but is more math than we know how to do. So we're going to start by just swimming for it, and it turns out that that's just enough that we're good, right? If we swam from it, if we just swam to shore from the center, he eats us. But if we swim from shore from the quarter mark, you'll see here that we're just slightly better than him, right?
So, now, how do you end this? All you have to do is just write the stuff at the top.
Yeah, the stuff at the top. You want to? What's the stuff at the top say? You say when you're doing this on a test, what you write is the stuff at the top. You have to say, what do I know from the loop invariant? Well, he's opposite of me. What do I know from the exit condition? I'm at the quarter mark. What is my action? I swim for it. What do I need from the post condition? I'm at shore without him. And then this bit right here in the middle, you have to prove that if these things are true, then this will be true, right? And how do you do that? Any kind of picture, hand waving, you just do your best. So how did I do it? I did this little calculation here, right? From the exit condition, I know that I'm at the quarter mark. So how long does it take me to get to shore? It takes me 3/4 time to get to shore. How long does from the loop invariant, I know he's opposites from me. So how long does it take him to come around to where I will be? It takes him pi divided by 4 time, right? Which is longer than me.
Okay, so I have a question. Sorry, I have a question about the exit condition. The exit condition, wasn't that for our past action, which is the one that swim opposite of him? Why is it still the same for swim for it? Isn't when we changed our action to swim for it, shouldn't our exit be our exit condition should just be when we reach the shore?
Oh. Okay. This is still the exit condition from when we started the loop, right? So if let's see if I can go back here, backwards somehow.
Yeah.
Right
like,
over here,
I'm wondering,
this tells me I'm doing a loop, and the exit condition tells me when I leave the loop, right? When I finish the second phase. And over here, the exit condition is not when I exit the program. This is the exit. This is sort of the precondition to the code after the loop, right? Imagine a piece of code that has a loop, and the code C is at the bottom after the loop, right? And so what's that code's precondition? The code's, what's true when I start code C? What's true is that the loop invariant's true because we just exited the loop and we maintained it. And we just exited the loop, so the loop's exit condition is true, right?
Okay.
And now that's what's true when we start the code C, right?
But isn't a code C like a loop by itself? So we need to have it needs to have its own exit loop, or
it could be a loop by itself. But in all the programs we're going to talk about, there's only one loop.
Okay.
Right. And so as you're maintaining the loop, maybe you need a second loop. So, but we will not talk about that second loop. We'll just say in English what happens, right?
Okay.
And maybe in code C there's a loop, but we're not talking about that loop. We're just saying in English, what are we doing? We're swimming for it.
So basically, I'm just kind of referring to the loop that I just exited. I exited because we were the 1/4. Okay.
Yeah, exactly.
Okay.
Exactly. This is what's true when I fall out of the loop. What's true? This and this is true. And then I execute this code. What's this code? Swim for it, right? And we know what that means, right? Especially if you draw a picture, you know what it means. And so you swim for it, and then you have to see, well, when I'm done swimming for it, by definition of swim for it, it means it is the shore. So by definition, I'm at the shore. And where am I? Well, swim for it sends go to the closest place in the shore. And then is he there? We have to calculate, is he there? Right? Does that make sense?
Makes sense.
Do we need to show the calculation how we got the exit condition, or that's fine?
You need to do three things. You have to tell me how I established the loop invariant, and you have to prove to me, right, this arrow here, what's that arrow there do? It says, assume we know the loop invariant, assume we know not exit, assume we do the code. Then you have to prove that you can do two things, that you can maintain the loop invariant will still be true, and you've made some progress. So how do you prove that? How do you prove that arrow? That if these things are true, then that's true? The way you prove that is something like this, right? And my feeling is that in an hour-and-a-half test, I would not expect you to do that on your own. And maybe if you had 24 hours, I would expect you to do it. But my goal is to give you a test that you could do in an hour-and-a-half. So, I don't know. I do think this problem is beautiful because I think you can understand it when I give you the solution. You can see how the solution is following the steps. But it really is solving a problem that's quite hard, right? I mean, if you think about, this is a pretty hard problem. I think it's harder than you could come up with yourself, maybe, unless I gave you really good hints.